I want to start off by talking about our friend, the get attribute protocol. I want to share with you a little bit more about what the MRO really does for us, how it integrates with this protocol, this being one of the most important core protocols in Python. I want to talk a little bit about what the descriptor protocol is and give you a particular sense of how the protocols in Python are designed. It's not really about finding a mathematically pure and elegant implementation so much as finding what works and solves most people's problems. And I want to tie that to how things like instance methods, class methods, static methods, and properties work. Why don't we take a look? Our first consideration is to just make sure that we have a strong appreciation that Python is implemented around certain protocols, which give us the ability to manifest a vocabulary that is provided to us. And this is what I mean by a vocabulary. Somewhere, somebody in the world told me that x plus y is a meaningful thing to do. In fact, if x and y are numbers, oh yeah, of course x plus y is meaningful. It's just the arithmetic addition of these two numbers. And they told me that this was so meaningful, this plus operation, that I could express it on things which aren't integers, on floats. Well, of course, x plus y, if they're both floating point numbers, is just floating point addition. I don't even see that there's much of a difference between integer addition and floating point addition, even though we know our computer does see a difference because our computer will represent both of these values, or all of these values, in a very different way and will implement these operations in a very different way. This plus operation is so meaningful that I can extend it to even things like complex numbers, where the amount of work that's done to add two complex numbers is literally twice the amount of work that's done to add two integers, because we have to add the real parts independently of the imaginary parts. But fundamentally, even though these three operations do completely different things under the covers, when I see x plus y, I say, yeah, of course, that makes sense. It just means arithmetic addition, and it follows all the rules of basic arithmetic. When x and y are no longer numerical values, but instead are things like collections.counter, x plus y, does that still make sense? Yeah, just add the two counters together. That's all accounts in one plus all accounts in the other, and sum them up. And if there's no corresponding value in one versus the other, then consider that count to be 0. If x and y are no longer counter objects, but they're numpy and d arrays and they're of different shape, well, of course, addition still makes sense. Even if they're different shape, I have my broadcasting rules. And if x and y are not numpy and d arrays, but are instead pandas series, I have my pandas equivalent of this idea of broadcasting, which is index alignment. The difference between x plus y when these are both integers and x plus y when these are pandas series objects with index alignment, in terms of the implementation, it is significant. The amount of code that's run to support x plus y when they're both series objects is enormous. And it is dramatically different than the code that's written to support x plus y when they're just integers. However, the core vocabulary, the idea of just saying x plus y and somebody looking at that and saying, I know exactly what you mean. Well, Python provides you with that vocabulary, gives you the ability to express yourself in terms of that common vocabulary. People look at that code and then say, yeah, I know exactly what that means. And you then implement this via the object model, via the so-called dunder methods, via the so-called data model methods. In other words, when you want to give meaning to the idea of x plus y on some arbitrary object, you implement add. And even here, I want this to be human representable. When I want to give some meaning to the idea of getting a human readable representation of an object, I write a repr. And as we've discussed previously, there are all sorts of rules associated with these, and as well as conventions. Rules, for example, that may constrain what you can return. Len, for example, must return a non-negative integer value. Conventions like repr should be, where possible, a way to reconstruct this object. And so we have a particular style of repr if we aren't pandas or numpy, which break this. Well, it turns out that even attribute lookup is a protocol. When we do object.a, this is a protocol. And we have the ability to implement this protocol. We have the ability to customize what happens when this protocol is invoked. We have the ability to hook into this protocol. We have the ability to tell somebody what it means to look up a part of ourselves for an arbitrary object. And we may even be aware of things like the getAttribute_ method and the getAttr method. However, there is a big difference between the so-called getAttribute protocol and the so-called add and len and other protocols in that where the totality of the add protocol, the totality of the call protocol are more or less invoked via these underscore methods are more or less implemented via these underscore methods. The get attribute protocol is much more fundamental and has some mechanisms that are not quite within what we can recreate in pure Python. The get attr underscore function and the get attribute function are really only small hook points within that protocol. Now, let's think a little bit about what happens when we invoke this protocol. When we have some object that is of some type where that type has an inheritance hierarchy, and we look up the .x, the .y, the .z of this object, and the x, the y, and the z can be found in different places, either as part of the instance state, or as part of a base class, or as part of another base class, there's some mechanism that's invoked by default that implements this lookup. With all of the protocols, there's usually some default implementation where meaningful. And so, for example, if I didn't implement repr, I would get the default repr, and it's not very readable, but it still works. If I were not to implement add, well, there's not really a default implementation of add. It doesn't really generalize to any arbitrary object, and so in this case, I'm forced to implement add. Well, for get attribute, or for the get attr protocol as we call it, there is a reasonable default implementation, and I want to show you a little bit about how it works and show you how it unifies a lot of concepts that might have been rattling around as you've been using Python these past few years. One important consideration that we should take into account when we're talking about looking up attributes on some object is the places where this could be found might not just be the object's instance state or its base class, but might be the base classes in some complex inheritance hierarchy. For example, our classical diamond inheritance hierarchy, where there's 4 possible places we can look, and it's not clear to us what's the order in which we look in these. But as we've seen previously, we have this MRO, method resolution order. When you define a class in Python, we statically determine as of class definition time, so this is a very soft sense of the word static, we statically determine as of class definition time what the order in which you resolve things, the order in which you look through these classes. And we must turn this into a consistent linear ordering. Therefore, certain multiple inheritance hierarchies may not be valid, and we won't even be able to define classes with an invalid inheritance hierarchy. The classical example for that is if we do something like this, there's no way for us to get a consistent ordering without changing how B and C are ordered at D. But here we can see we have a consistent ordering, this MRO, D, B, C, A object, and in fact, that's the order in which we'll look through all of the base classes in order to find something. Now, I want to share with you one more consideration before I show you how all of this works. One important thing to think about and to maybe scratch your head a little bit about is when we have instance methods in Python. These are methods that operate on some instance state. They take an implicit argument that you explicitly refer to. Personally, I've always hated the idea of calling this implicit self or explicit self because it's explicit in the sense that unlike in JavaScript or Java or C++, you have to have an explicit argument, but it's implicit in the sense that it's passed in, but you're not explicitly passing it in. So I can never remember, is it implicit self or explicit self? And I feel like implicit and explicit, well, it's both implicitly passed in, but explicitly referred to. But whatever the case may be, when we have some function on some class, it takes this parameter self that references the instance that we're operating on. And when we call this function, we can see it's being passed the self parameter without us explicitly having to pass it. If we do t.f, so if we try to call this function from the class, not from the instance, you can see it errors out telling us you're missing an argument. But one thing we may know is that object.f is strictly equivalent to t.f passing in the object explicitly. We can refer to this function directly, and we can pass in that instance state directly, and everything should work exactly the same way as if we'd called object.f. If we take a look at object.f and t.f, we can see something kind of interesting. And if we go back to the Python 2 days, we'll see this distinction even clearer. Python 2 used to make a much clearer distinction between what they called bound and unbound methods. In Python 3, what we can see is object.f is not the function that was defined here. It's something that's been done to the function. It's the bound method t.f. Whereas when I look at t.f, this is the actual function. It's actually this function right here. In addition to all of these, we have other operations that apply to the class. We have things like class methods, we have static methods. And so here we have an example of a class method. We can call object.f, and instead of being passed the instance, it's passed the class. We can do t.f, which also works just the same way as object.f. And if we want, we can dig into that function for its underscore underscore func underscore underscore method, or attribute, I should say, and explicitly pass in the class in a similar way as before. And here you can see in these two cases, we get a bound method. In this case, we get a function. Finally, we have static method, which seems to work identically in both of these two cases. And when we actually look that up, we can see there's no wrapping that's being behaved. You're getting that actual function out. Finally, we have property. And property is some sort of hook that we've put. It's some computation that we're hiding behind an attribute access. It looks like an attribute access, but it's actually a computation. And you can see when we do object.f, well, it computes this. When we do t.f, it doesn't. We cannot explicitly pass in the object. We can't call this property in that way. But if we dig enough, we can find the fget and call it directly. And if we investigate what's going on behind the scenes, we can see this wrapping is a little bit hard for us to unwrap. Even though these look like very different things, and even though our motivation for where we use each one of these, property, class method, static method, instance method, are very different. Class method, for example, 80% of the time being some sort of factory function to do that nominal decomposition of a bounded modality, whereas property is more about not doing work up front if you don't have to. Well, whatever the case may be, it is turns out, behind the scenes, that the implementation is actually largely very similar. One other thing that I want to share with you is the following. If we have a class, and for that class, we have some function that we have defined outside of that class, surprisingly enough, we can put this function back into the class using this f equals f. This is a very weird little scoping issue that comes up. We can actually do imports in class bodies. And in the class body, when we do an import, we can actually bring something into scope. And when we bring something into scope, it'll actually appear as a method. So these two imports will actually introduce a G and an H into this class. And we can invoke f in 3 different ways, and it works. We can invoke G in one of these ways, but in the other way it doesn't work. But even though the import that's creating G and the import that's creating f look identical, there's a difference here. For whatever reason, we can invoke this function G on the instance. Sorry, we cannot invoke this function G on the instance, but we can invoke this function H on the instance. There's some mechanism behind the scenes that's making this all work that just may not be clear to us, that might be something that is existing outside of where we expect to look for. And in fact, the unifying idea behind all of this is the get attribute protocol. The get attribute protocol is a protocol like almost any other, with the exception that there's a couple of things that occur at the interpreter level that are almost impossible for us to really mock up in pure Python. But if we accept certain simplifications, I can show you exactly how all of these things work and how they tie to the idea of the get attribute protocol. And the way I'm going to do that is I'm going to set myself up with an inheritance hierarchy with 4 different attributes I can look at, x, y, z, and w, where one of these is a property, one of these is an instance state, and 2 of these are class level state. And I'm going to try to implement getAttr myself. And so here you can see my correspondence between the dotted access, the top level get attribute function, and the built-ins, which basically is equivalent directly to the dotted access, except you can provide a default if the thing doesn't exist, and my custom implementation. And what we'll see as we go through this is how the custom implementation actually works. We won't be able to handle certain things. For example, when we're looking at this, we will not be able to handle slots. There are some mechanisms that are just simply impossible for us to really mock up at the pure Python level, but for the majority of classes that we deal with, we can actually mimic the behavior of this protocol and understand what actually happens when we perform an attribute lookup. The very first step, and we know this, is when you're looking for an attribute, you look in the instance state, and the instance state takes precedence over everything. One thing that you might know is that for regular Python objects, they have a special attribute that represents the dictionary of all the instance state. Slots disables this, but for the majority of Python objects you work with, they have this underscore underscore dict underscore underscore that gives you all the instance state. And so what you could say is the very first step of this protocol is just to look in this location and if the thing is found in that location, to just return it from that location. And you can see we've managed to make one of these cases work. We could apply the same logic to the type. We could say if the attribute is found on the type of the object, then we return it from that dictionary, except this isn't going to work for anything that's in a base type. It'll only work for the direct type. Instead of looking at the type of the object, why don't we iterate through all the classes in the object's MRO? And remember, the MRO is specified at the type level. It's not specified at the instance level. So we have to first figure out what the type is, get the MRO from the type, and look this up in these cases. And if we do that, and I'll fix one of my formats here, just so you can see this. Let's fix this format here just for a second. You can see I managed to get the other ones working. The question is, how does that property work? When I look up that property, what's actually triggering the execution of that property? Well, it turns out that the getAttribute protocol is largely fairly simple. And there's maybe 2 hook points associated with it, and one additional consideration. Whenever you're looking up an attribute, you're basically following the MRO for the majority of your time to figure out where to find this if it's not in the instance state. But if you happen to find something in the MRO or in the classes that comprise the MRO, and the thing that you find looks a certain way, then you do a certain thing. In other words, one small consideration that we add is we take a look at what gets pulled out if we found this on the MRO. And if the thing that got pulled out has a special named attribute, get, what we return is not the object itself, but the consequence of calling this get method. We're going to call it with a couple of parameters. Here, I'm going to call it with these 2 parameters. And you can see that's all we need to get the property to work. To a large degree, the getAttribute protocol is as simple as any other protocol. It's just a sequence of actions with some hook points associated with it. And when we talk about things like the double_getAttr function and the double_getAttribute function, we can kind of mock up where those hook points are. It's going to be a little bit hard for us to implement them completely. But what we can think is there's one more hookup here. If there is a getAttribute that exists at any one of these levels, then what we do is we first check that getAttribute and do what that getAttribute says. And so there's a hook point at the very beginning before the protocol is even invoked to do the getAttribute stuff. And this isn't going to quite work because there's a little bit more mechanics to actually making this work. And if we didn't find what we were looking for through the normal mechanisms, then we look through the MRO, or we look through the classes that comprise the MRO for a getAttr function. This is just a hook point at the very end. But here you can see almost the totality of the getAttribute protocol, ignoring certain things like slots, but this is for the majority of your objects. You look in the instance, you look down the MRO. If the thing that you found in the MRO looks a certain way, namely has a get method, the so-called descriptor protocol, then you invoke that as opposed to returning the thing. And at the very top, there's a hook point for getAttribute, and at the very bottom, there's a hook point for getAttr. And that's really pretty much how all of this works. Knowing how all of this works, we can actually then determine how it is that instance methods, class methods, static methods, and property all work. Here, I have a simple class that has an instance method, a class method, a static method, and a property. And note that the instance methods in Python, they don't require any specific annotation. They don't require a specific decorator. It would be very clumsy if we had to do instance method every time we defined an instance method. So we can think that when we mock this up, when we create a parallel implementation, we'll have to be a little bit more explicit that we're using our parallel implementation to match up with the default behavior that we see here. If we run this code, we can see all the different ways that we can access each one of these things, either through the instance or through the class. And let's see if we can actually implement these following what we've learned. Here, we're going to first take a look at the instance method case. And so in the instance method case, here we have our normal instance, and here we have our mocked up version of the instance method. And you can see those are the 2, actually I'll call these 2 here. These are the 2 ways we can call this instance method. Either we can call it on the class passing the object explicitly, or we can call it on the instance without passing the object explicitly. And really, instance method is really just this class with this get method. And what it returns is it returns a brand new function that forces the first argument to be your self parameter. This is how that self parameter actually makes it in. The get attribute protocol defines a little branch off to the side that says if you have a get method, I'm going to go through that get method to dispatch to where we go. And I'm going to provide that get method with two arguments, the instance and the owner. If it's an instance method, we just pass in that instance as an argument, and we're not calling this function. We're just returning a brand new function that forces this to be the first argument. We're binding this with a new function. We could use something like functools.partial to do something similar here, but I like this implementation because you can see it's very clear. We're just returning a new function. Or if we're retrieving this thing from the class, therefore the instance isn't set, then we don't pass anything here. We just return the raw function. That's all instance methods really do, and that's how that self parameter gets in there. And so if we look at our implementation, or the consequences of our implementation here, we can see we've matched this up with the official version exactly. Now, we can take a look at class methods. Here's our official implementation of class method. Our implementation of class method, you can see here the code looks kind of similar here. It's just a mock-up of a class method and our custom class method. Here, our class method in the get just passes in the owner instead of passing in the instance as a first argument. And you can think that when you invoke this descriptor protocol, you're given the instance or the class, and you basically either return a new function, hard coding, forcing that first argument to be the instance, or forcing that first argument to be class. Class method works basically like instance method, even though they're used for very different things. So you can see here, all of this matches up. For static method, the answer is even easier. Here's our simple static method example. Here's how our static method works. For static method, we either don't have an __.get, or we just return the function itself directly. We don't return a brand new function, we just return the regular function. And when we implement that, we can see all of our static methods and all of our implementations work identically. And then finally, for property, instead of returning a brand new function, we just call the function that we saw. And so this is how property works. All it does in that descriptor protocol is it says, you know what? I saw this get method. I'm going to call that get method, and it just calls the function as opposed to returning a bound function. In Python 3, there's no longer a distinction between unbound methods and bound methods. Instead, in Python 3, all functions that are defined in pure Python are automatically given as part of their construction a get method. If we do a dir on any function that is written in pure Python, we will see that it has a __ get, which means if we put this function into a class body and via the get attribute protocol, we find this function in a class or a base class, then we trigger this get method. The get method by default does this mechanism that my mockup of my instance method does. It replaces what you retrieve with some manipulation of what you retrieve, basically a brand new function that's bound, has that first argument bound, has an instance argument bound. Class method is basically a mechanism that says, okay, don't replace that first argument with the instance, replace that first argument with the owner. Static method basically says, just give me back the original function, don't actually do anything magic. And property says, just call the function itself. This is why, in this example, we see a very slight difference between this G and this H. Here, I'm pulling in JSON dumps, and I'm pulling in itertools.repeat. The JSON module is written in Python. The itertools module is written in C. Because the JSON module is written in Python, the function dumps in the JSON module has that get automatically. And when I look that up via the get attribute protocol, and I find it on the base class or the class itself, the immediate class itself, I trigger the descriptor protocol. Because the itertools module is written in C, the functions that are exposed from the itertools module do not have that __ get, which means when I find them, I just return the raw object itself, which is why this works when I pass it one argument and everything is fine, but this fails because it tries to insert the self parameter following that get attribute protocol and says, oh, you passed me too many arguments. And you can see here, it takes one positional argument where two are given. Well, the first argument was that self parameter that was introduced by the Python function's default implementation of __ get. This is how they simplified how instance methods work in Python 3. And you can see where just some understanding of a fairly simple protocol, a fairly simple flowchart with two interesting hook points, that get attribute hook point at the beginning, the get hook point at the end, and one interesting little carve out. Oh, if the thing that you found, and critically, the thing that you found on a class, not on the instance, happens to have a get method, then you invoke some particular function as opposed to returning that. This is why, for example, you cannot add instance methods to classes at runtime and still have that self parameter implicitly added in, because this only is triggered when you look this thing up on the class. It is not triggered when you find this thing on the instance itself. Here's our conclusion. Python is designed around protocols, and the code that we write with Python is basically designed around how do we implement those protocols to implement this vocabulary. Attribute retrieval is a protocol like any other. It just has its own rules and its own hook points. Python's implementation of these protocols is not meant to be mathematically concise, mathematically comprehensive, mathematically elegant. It's basically, here's a flowchart, and at what points of the flowchart would it be useful for me to hook something in to get some effective behavior out of this? In order to support the effective behavior of instance methods, class methods, properties, and static methods without adding too much mechanism to this protocol, they came up with that one little carve out, the descriptor carve out, and that's how this all works. And this is why everything else works the way it does, why you can't add bound methods or you have to do something special to add bound methods to instances, why it is that these different methods are able to have their implicit arguments passed in directly. It comes down to where something is found, and why it is that there is a hidden distinction in CPython between functions that are written in Python and functions that are written in C. They actually will work differently when they're added to a class body.